get this thing going. The first thing I want to do is a quick recap from yesterday's stuff. So one thing I did want to highlight that I didn't really get to because we were kind of dragging on a bit. There's really good animations here that are going to outline for you, especially this one. Wait, I'm not sharing my screen. Here we go. So especially this one, the one that says science.smith.edu, and there's one for today as well. Maybe I'll just open it here. I was looking up some details. Here. So this is really good. You can click each of the steps and it'll kind of show you what happens at each one. There's a bit more maybe detail, some couple of terminologies, but it's a good animated. So when I'm just sort of yelling and saying bing, 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 that's what's happening. You can see the actual movement of electrons taking place, right? Or splits water, bing, 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 right? Donation of electrons and so on. So you can, it's a bit nicer to see it happening.
What's the antenna complex?
It's just, that's what they call all those chlorophylls around it.
Oh, the ones that you drew inside, but that one is outside.
Around the, yeah, it's showing trying to give you a inside view.
Okay.
But that's what's it's like a satellite dish, accepting the light. Yeah, so these animations are really good. And so today's one, there's a similar one today that, oh, how do you reset it? Oh, no, you don't, you just press stage one. I'll go through this after as well. But from yesterday, so quick recap. All right, this is, remember, the reactions that take place when there is light. So the first thing we have is light shines on photosystem 2 and photoactivates an electron, meaning it excites it to a higher energy state. As well as, in addition to doing that, it also helps to do photolysis, which is the breaking of water, splitting of water, so that you can replace the electron that was super excited. That electron then starts to travel from protein to protein along this electron transport chain, losing energy as it does so. We can use the energy that it's losing to pump protons or pump H+ ions from the stroma into the thylakoid space. What does this do? Yep.
Quick, just to clarify the electron transferred, it's called, how does electron flow from the PS2 to the protein pump? Is this process is called electron transport chain?
Yep.
Okay.
Yeah. So getting moved one protein to the next is the chain. So they're handing it off.
Okay.
Like a relay kind of. And you could almost say, how in respiration, we said oxygen is the one sort of pulling it, right? It's like the terminal acceptor. In this case, at the end, you have NADP+, which is sort of not really the same idea, but the ferredoxin, where that happens, is kind of pulling it that way.
Okay.
So we accumulate, right? Here we go, hydrogen ion accumulate, high concentration. That creates a concentration gradient. So they flow through ATP synthase, and that spins the ATP synthase protein, enzyme, and generates ATP. The second part, or kind of the middle, I guess, part, is that there's light that gets captured by photosystem 1, which further re-excites this electron that showed up here, and brings it to ferredoxin. That energy, or that energized electron, then becomes part of the reduction of NAD+ to NADPH. As a bonus, you get these hydrogen ions get incorporated into that, so it keeps this area low compared to the inside, so that you have maintained this gradient. So by maintaining the gradient, you could continue to produce ATP. Any questions before we move on? Okay. So one thing just for interest sake, to link us back to the SL topic is if you notice here, these like little additional bumps in the action spectrum, right? Or how effectively photosynthesis takes place. What that's an indicator of is the two different photosystems. And if you look down here in the bottom right corner, it shows you a separated absorption spectrum of two types of chlorophyll. So usually we just say chlorophyll, but really there's types of chlorophyll and there's other pigments as well. If you look at two different, like chlorophyll B and chlorophyll A, usually we just talk about them together and just say chlorophyll, but in fact they're their own pigment, and they have a different absorption spectrum, so they can absorb different lights at different efficiencies. But also this kind of shows us that like because those chlorophylls absorb different wavelengths, they can give us these like slight variations in the action spectrum because they have peaks at different points. So what you have here is, for example, here, PS2, photosystem 2 has this peak of activity of a different kind of mixture of A and B, versus photosystem 1 has a separate combination of A and B. So it has like maybe more chlorophyll A, whereas photosystem 2 has more chlorophyll B in it, something along those lines, which is why we get this like difference in that it's not like a smooth curve here, but it's actually got two peaks. It just means that the two photosystems are like different mixtures of types of pigment, and because of that, you get variation in the action spectrum.
Mr.
Mm-hmm.
Are we supposed to know the rough shape and position of the
yeah, so that's a good question. I actually, it's good that you asked that, because I was also double checking to see if you needed to know like this detail, and apparently not. I specifically looked at a mark scheme to see like a question that said like draw the action spectrum of chlorophyll, and it said 2 peaks, one towards 400 and one towards like 700-800. So it didn't say like also this bump here. That was not part of it, because this is an SL objective, right? This is an SL objective, so this bump stuff is not, is an HL detail, but wouldn't be tested in terms of this graph.
Yeah.
Okay. So now we're moving on. So we said that the point of the light-dependent reaction is to gather materials, right? If you've ever heard that, there's like a like, what do you call this? Like fable? No, like a story, like a children's story where like there's grasshoppers and the grasshoppers, and like some grasshoppers are super lazy, and then the one just works really hard, even though it's really hot out or whatever. And then anyway, I don't know.
Isn't that a children's fable?
Yeah, could be. The point of the story is like the grasshopper who worked when it was sunny and nice, he had like food, and the guy who was like, oh, it's sunny and nice, I'm just gonna play around, he had nothing, and then he died or something. Whatever. How does that relate to this? It relates because a plant, when there's light, will make stuff that it can use when there's not light, right? So what is it? When it's sunny outside, make hay, or something like that. Something about hay. I'll look it up later. The point is, two things were made during the light-dependent reactions. What are they?
NADPH.
And?
ATP.
ATP. So we're now going to use those two things in the light independent reactions, right? So now when in the reactions that do not require light, these two things are going to be kind of the power that drives those reactions. When you have light, that's the energy source, right? So when there's light in the light dependent reaction, you have a source of energy which is the sun or a lamp or whatever. That's going to drive the excitement of electrons. When there's no light, you need something else to help the thing go on, right? Otherwise, it stops working. So the source of that energy, if you will, is going to be ATP and NADPH. Okay. So this has many different names. Okay. You might see it called Calvin cycle. You might see it called the dark reaction. You might see it called another name that it gets. I can't remember. I thought there was another. Just like carbon
cycle.
Carbon fixation, maybe something like that. Anyway, there's many names that you might find for this process, but we're going to call it Calvin cycle, okay? Because Calvin was the guy who discovered this. So let's go to this one. Okay. Right. So hopefully you have a little space to draw / write. And
on the previous one?
No, next. Blank. New. So we're starting with let's write it in black because it means that there's no light there. Light in, I got used to writing with this tilted. No, I don't like that at all. Independent okay, aka Calvin cycle. Why can't I write properly? Okay, so the reactions that are going to take place, whether or not there is light.
But technically, it also depends on light because it needs the light-dependent reaction to happen before it can happen.
Very correct. Very correct. In this corner, you're correct. So without the stuff that happens with the light, you can't really do this. That's correct. Although, yeah, right. I don't remember what color we used. Oh, I think it was gray. So I'm just going to put in the corner here. Here are the things that we were able to bring, right, from the light dependent reactions. Why does it look like the pen leaked? Where did it go? All right, so let's begin. We're going to begin with, remember last time we said there's not yet, the whole point of this, we've always said photosynthesis, we're making glucose, right? Photosynthesis produce glucose and oxygen. So where does the organic material come in? Once again, we got to start with this like chicken and egg situation. So it has to start somewhere. We're going to pick one place to start. We're going to start up here with a 5-carbon. A 5-carbon. That is just awful. Try again. A 5-carbon molecule. Okay, 5-carbon. That is called RUBP. Ribulose bisphosphate. RUBP.
RUIP.
Okay, not quite, but something like that. And the very first reaction that takes place is a process that's going to bring a carbon from over here that's a part of CO2. Remember, CO2 plus H2O gives blah, 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 blah. Here's where the CO2 that has entered the plant through the stomata and now has made its way into the chloroplast is going to incorporate into this RUBP molecule. Really, guys, 5 carbon plus 1 carbon from carbon dioxide gives yes, get your GDC.
5, 6.
Fantastic. Now, the 6 carbon molecule, you can draw it, but it's really quickly, it doesn't last very long, and it's going to split, oops, it's going to split quite fast into two 3 carbon molecules. Okay, and those 3 carbon molecules, so we kind of ignore the 6 carbon, it's very unstable, to 3 carbon molecules called 3 PGA. I believe the name is phosphoglyceraldehyde. Anyway, the name is not super.
GPA.
PGA like the golf tournament. PGA. That's the name of
2 and 3 PGA, or is it just 3 PGA?
the name is 3 PGA, but there are 2 of them.
Oh, okay.
Wait,
The name is 3.
5 carbon molecule. Is it called RUBP or 5C RUBP?
Just RUBP, sorry.
Okay.
Let me actually, yeah, good point. I'm going to change the size of this so that it's consistent. So RUBP and okay. Now we should, before we go too far, we should name this. When you take this CO2 and you add it to the RUBP, that's a process called carbon fixation. Carbon fixation. You are fixing that carbon onto an existing molecule. Carbon fixation. So through carbon fixation, you end up with these 2 molecules of 3 carbon called 3 PGA. So far, so good? Okay, I will take that as a yes.
Wait, do we need to know, like, the PPT say it's catalyzed by something? By
Yes,
Rubisco.
of course. I nearly forgot. Thank you for reminding me. I'm going to put that in a special color, green. Okay.
No.
Yes, thank you, William. Very good. Rubisco.
Oh yeah, and where does this occur? Like,
This is
Right.
occurring in the stroma, right? Because remember where the ATP is produced in the stroma and the NADPH was produced in the stroma. Let's go back up.
Stroma is
So-
the empty space, right?
Yeah, so here, stroma.
All right. Oh, so it's just outside. It's just convenient.
Correct. And that's where the enzymes are, because the ribosomes are out there. So ribosomes are needed to make the enzymes and blah, 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 blah. So yes, that is a good point as well. This is all happening in the stroma. Okay. So Rubisco, very, very, very important. This enzyme, you learned about it in the enzymes, in the proteins topic. Okay. This is what, this is the enzyme that is responsible for actually taking the carbon that's part of carbon dioxide, which has no, or is completely inorganic, and shoving it onto an organic molecule. That is how this takes place. Without Rubisco, we don't have this production, okay? So Rubisco is the enzyme responsible for basically all of photosynthesis being able to happen.
The 6C and 3C, is it broken just because it's unstable, or is it because of?
Correct, unstable.
Okay.
Okay, so Rubisco, very, very important. Can I remember the full name of Rubisco? I usually use this because it's very scary. It's a very, very long name, so you're lucky that you only have to remember that it's called Rubisco. I'll look it up later, or someone can look it up. Okay, so yes, thank you for stopping me before I got too far ahead. So 5-carbon REBP uses the enzyme Rubisco to fix inorganic carbon from CO2 onto this REBP, forming a very brief moment 6-carbon molecule, which quickly splits into 2 molecules of 3-PGA.
God, that's the name.
Yeah, what is it?
Ribulose-1/5-bisulfosphate carboxylase. Yeah.
Carboxylase.
Carboxylase/oxygenase.
Yep.
This
I
is
told you.
science.
It's ridiculous.
This is science.
This is science, right? But Rubisco sounds super cool. So just be happy that you don't have to remember that. There's always positives, guys. Okay.
Ew.
There you go. All right. So now this 3-carbon 3-PGA is going to get converted into another 3-carbon molecule. And because we don't want to overcomplicate things, we're not going to show all the like really specific changes that take place. We'll just say that it's another kind of form of the 3 carbons rearranged differently. And this time it has a name. You can say that it's still 3-carbon. Right? And the name for this is G3P. Okay, G3P. Now, how does this, what is actually changing? Well, there's going to be some of our old friends from up here in this corner. They're going to get involved. So you're going to have ATP. It's going to provide some of the energy needed to make these changes. Okay. There's actually going to be 2 of those. The 2 ATP. and
Is it
2 of
because
this.
there's 2 electrons before?
And I mean, there's 2 of those things, right? 2 of the 3 carbon things.
Hmm? Oh.
Like 1 ATP for each of the 3 PGAs. And you're also going to use 2 NADPHs.
Mr. Miller, I assume the ADP plus PI goes back to the light dependent one.
You would assume correctly. And the same thing is true for these, for this one. Right? So the NADPH has the reducing power, right? It's getting oxidized now. So it's able to reduce the 3-PGA. The ATP provides some energy to change around the molecular structure of this carbon compound and rearrange it into whatever G3P is. Now, here's where things get a little bit wild. At this point, we have a bit of a mathematical problem. Yes? Can anyone just verbalize what's the problem we have here?
There's
Problem. 3 plus 3 equals 5. Yes.
Yes, that's perfect. There's no problem though. No.
6 equals 5 is false.
Correct. 6 equals 5 is false. We have a very serious issue because 6 equals 5 is false. So,
But really?
how do we solve the problem that 6 does not equal 5? Here's where things get very cool. We're going to say, I'm going to grab a different color here. Let's go with purple. Okay. This is showing the Kelvin cycle in one term, right? In order to make 6 equal 5 or 5 equals 6 or whatever, we have to assume that this cycle is turning a lot, right? And every time it turns, you add a new carbon from CO2, and then it turns and somehow regenerates into 5, right? Somehow 6 is becoming 5, even though we're adding 1 every single time. That means what? What has to be happening also?
6 cycles.
Yes, but if you did 6 cycles, you would just keep piling things up, right? What's another thing that has to be happening? We're adding carbon all the time, but somehow we're ending up with the same number.
The word is right there. I just can't say it. It's right there. What is that word?
I mean, it's really just, I mean, what would you need to do?
Decarboxylation.
Ah, okay, that could be an option, but that's not going to, that could work because you're saying, why not remove some carbon dioxide? Then you can come back to the same number. But then you're just getting, like, you're just doing the same, like you're adding it and then taking it away. So you're really not gaining from that, right? It doesn't help us to do anything.
Mm-hmm.
How about let's ask a different question. Where's glucose?
In the plant.
Isn't the whole point of this to make glucose?
Really?
The whole point of photosynthesis is making glucose, right?
Yes.
Yes. So somewhere in this cycle, we have to get glucose. And glucose can't get stuck in the cycle. because then you would never have glucose and it would keep breaking apart and being reformed. So we're actually going to have some of this G3P product is going to leave the cycle. Okay, it's going to be taken out.
Wait,
of
what
the
do you mean
cycle.
by some?
Hmm?
What do you mean by some?
Yeah,
Like, is it
that's,
like random?
I'm getting there. Don't worry. We can't take all of it because then the cycle ends, right? The cycle will stop turning. That's impossible. We can't leave it all there. Then you're going to have log jam and you keep adding and it's no longer a cycle. So we're going to take, bear with me, 1/6 of all the G3P that's made is going to be taken out of, I'll write that a bit more clearly. Okay, 1/6 of all the G3P that's made is going to be taken out and is, okay, so let's say we have a G3P there, but that means every time you take one G3P, that means 5 G3Ps, okay, and I'm just going to do this on the side here so it doesn't drive you nuts. That means 5 G3Ps are going to carry on. How many carbons are in 5 G3Ps? 5 times 15. 15 carbons, right? So that means how many RUBPs can I make with 15 carbons?
3.
Boom. So what we're saying is for 1/6 of the G3P being removed, 5/6 continues as part of the Calvin cycle to reform RUBP. In other words, in order to make one glucose molecule, and glucose molecule will start after you get one G3P here, and then you add another G3P eventually. Let's do this. You get a molecule called glucose phosphate, which is like one step away from becoming regular glucose.
The 1/6, is it like 1 out of 6 carbon, or is it 1/6 cycle? Like what?
1 out of 6 G3Ps.
1 out of 6 GC. Oh.
Okay, so for
The
every 6 G3Ps that we make, one of them is going to go out of the cycle and become part of glucose phosphate. The rest of them will continue on and
one
be
cycle
rearranged.
only have 2.
Yes. But we can assume that it's not just happening like once like this, but it's many times they're happening.
Okay.
And really, for every time that this turns, you're really only adding 1 carbon, right? So in fact, to make 1 G3P, you need 3, let's think of it this way. You need 3 CO2s, right? Because if you're going to take a carbon off, you need to add one over here. So really every turn adds 1 carbon. So that means to get 6 carbon, you need to turn the cycle 6 times. And how come that works? It works because when you're left with, what you're left with after taking 1/6 can still be rearranged by a factor of 5 to make RUBP. Because you will have, if you do this 6 different times, how many carbons end up in G3P? You'll have 3 times 6, which is 18. Right, 18. From 18, take away 3, gives you 15. Oops, 15, and then the 15 can carry on here.
Does it always start with 3 RUBP?
No, that's just the sum. I mean, like, again, like start and finish is kind of arbitrary. It's kind of arbitrary, right?
Okay, so we just have to know that RUBP and then this whole thing.
It just has it just explains how you can get to a 5-carbon molecule when you have only
6.
three carbons left. Because if I take one away, then how do I go from 3 to 5? Impossible, right? If I do this twice, okay, so can I go with 3? No. If I do it twice, can I go with 6? No. If I do it 4 times, sorry, can I do it 3 times? 9, can 9 become 5? No. Can I do it 4 times? 12? No, cannot. Can I do it 5 times? Yes, I can.
Okay.
Right?
All right.
And it's not five times, but you need 6 turns to get the 5, obviously. Okay.
1, 2.
How do we feel about that? Oh, there's one thing missing. We forgot one thing. To power this rearrangement, to go from these 15 randomly arranged carbons into 3 organized molecules of RUBP, it's going to cost us a little bit of energy here. I knew it looked empty on that side. It had to be something.
So 3 ATPs used.
Yes, let's say that, sure.
ADP, glucose, phosphate. Wait, so 6 carbon gets taken out, right?
6 carbons get taken out after 6 turns, yes. So basically for every turn, you're adding 1 and also taking 1 out. Because you were right, you said decarboxylation, right? That would work because you add a carbon, take a carbon out. Then what you're left with is what you started with. Nothing changes, and that's essentially what we want, because we want to keep always finishing with / starting with 5-carbon RUBP. We should always have 5 there. So if you go 5, add 1, some stuff happens, take 1 away, we'll always end up with 5 in the end.
Okay.
Right. So suddenly we have glucose, right? We also have the two other aspects of photosynthesis that we've always talked about. CO2 gets used here, and we come out with what will eventually rearrange. Right now it's a straight line, but we'll rearrange into the correct shape, get rid of the phosphate, and turn into glucose. Eventually that will become carbohydrates, it'll become cellulose or whatever, starch, etc., etc., etc. And that is the Calvin cycle. Wow. Any questions about the drawing and the process before we move on?
Am I stuck?
No, I don't think so. Okay, then let's go back to this thing.
Oh no.
All right. So to finish off, you can go through the steps again. And again, like I said, this animation is really good. It gives, maybe it's easier to see the math if you look at them. If you start with, for example, 3 like this, so you can see how it's breaking down and adding, fixing the carbon, right? So this does 3 RUBPs at a time, giving you 6 PGAs, and then you keep going. You can see the expenditure of ATP for each of them. You get the point. Okay. Anyway, so you can do that on your own. Okay, so there is the summary. Yeah, summary here. As Michael mentioned, of course, the NADP plus will go back to the light dependent, keep going back and forth exactly the same way as the electron carriers do in cell respiration. Here's an example of, you know, like a 10-point story, maybe a little bit less than a 10-point story, but that same idea. I really like the box that's there, the yellow box. It's really useful, right? The point is that, you know, not just to memorize every single thing that happens, but to be able to relate these two things, right? The reaction and to connect them. You know, one, connect them between the light dependent and light independent. Like, how does this, right? How is it connected to the two halves of this process? Then also make connections between my respiration and photosynthesis. What similarities are there? What differences are there? Because there really is a lot, and it helps to know the common aspects of both, because it's almost like you have to learn only half of it. Okay, so we come back to our sort of structure and function here. So now we can see sort of where these things come into play, right? So we know that all those proteins are embedded in the membrane. So the electron transport chains are happening all along here in these tiny spaces in the pockets of the thylakoids, or where you build up that high hydrogen concentrations. In the stroma out here, this is where all the other Calvin cycle reactions are taking place when there isn't light available, or even when there is light available, that could be happening. It doesn't mean that there has to be no light, right? So dark reactions, quote unquote, dark reactions can happen all the time. It doesn't have to be dark. And that's where your enzymes are going to be, and so on. Oops, what's going on? There's only 11 people here. It's just 3 people.
Is today SL?
It's still HL. Valen dipped. Interesting. So we keep going. Similarities and differences, we already did that. We've got this, we already did that. All right, and our last little bit here is one of these nature of science things. So Calvin, right, the guy after whom this cycle is named, has a very famous experiment. Okay, and you know, usually the sentence that I say is, I still have never seen this come up on an exam. This is the opposite sentence. This has been on an exam before, and it's kind of ridiculous because it's such a very it's a very random, very specific experiment to talk about. But I've seen it happen. It's been on on MCQ, just out of nowhere. So stuff like this happens, even though we just kind of brush it aside. You never know what might come up. So what they want you to know is sort of, how did Calvin discover or think that there was a cycle going on? And one of the ways that he did that was trying to trace the different organic compounds that were formed in the stroma throughout the cycle. Now, obviously, like just like the other thing, we've skipped a bunch, right? If you look up real Calvin cycle, there's like a million different intermediate compounds going on. We just drew 4 of them. So there'll be a ton more in between that we've ignored. But in order to try and identify them, Calvin did this experiment, okay? And the experiment goes something like this. So he uses an algae, okay, called chlorella, and he puts it in a very special flask. And this was the question. It was like, what is like something stupid, like what is the name of the flask that Calvin used or something? Anyway, it's called the lollipop flask.
What?
It's ridiculous. Or something like who used a lollipop flask in their experiment, or I don't know. It doesn't matter. Something silly like this. But anyway, so this lollipop flask, you can see the picture there. It's a very thin, like circular flask. So it has like flat side, and then skinny side. So imagine just like a thin circle that is a flask. You can fill with whatever you want, fluid. So the lollipop flask or lollipop vessel is filled with this water and chlorella. So this is photosynthetic algae. Okay, so what he does is he allows the algae to photosynthesize. So gives it carbon dioxide, gives it light, and just lets it be, lets it photosynthesize. And then at some point, he introduces instead of the normal carbon dioxide, he introduces a radioactive type of carbon dioxide. Now, why is this important? Well, radioactive isotopes can be traced, exactly, okay? At this time, when he's doing this experiment, tracing maybe was not the right word, but what they could do is they could put it on like X-ray paper, and the radioactivity would kind of burn, like wherever it was, it would burn a little patch to indicate where the radioactive carbon was. The other thing that it's trying to do is it's trying to do like a timeline, right? So he's trying to see if carbon is being fixed, meaning it's being incorporated into these compounds, what gets made first, or like what's the order of these molecules and how they're made. So his idea was to try and trace them using not just, so that method of radioactivity plus X-ray is called autoradiography. And then he also used chromatography, which we talked about in the SL topic, of separating things based on their size. So you put like everything you find, you put in fluid, and then like run this solvent, which is going to separate all of the molecules by how big they are. And what you should see is, right, what moves up to the top fastest? Well, smaller molecules should move up to the top fastest, or something based on density or what have you. And so this is what he was trying to do. And what did he find in his results? What he found was that, so if you look at this picture, you can see 5 seconds of photosynthesis versus 30 seconds, okay? So what he's trying to do is he's stopping the reaction after 5, taking a sample, and he wants to see where did the radioactive carbon get sort of joined into the organic molecule first, right? And he sees that there's a dark spot right here, and by chromatography, he's able to say like, oh, if it has like this size, like because it moved this high on the chromatogram, then this is what this compound must be, right? So he can name it and label it. And what it tells him is this is the first compound that got made because it's the darkest spot. So that means all the radioactive carbon that was introduced first went to make this. And we know that that's PGA, and we know that that gets fixed right at the beginning with Rubisco. If you leave it for a while, you can see that the radioactive carbon then becomes part of all of this crazy stuff, which means then it's forming a bunch of random other compounds. But it tells us that it started here, and then all of this carbon eventually became a part of all these things later on. So what's the point of all this? It's that experiments are cool, and developing new techniques to learn stuff is cool, okay? And and that Calvin wouldn't have been able to do this if not for these two different techniques that maybe he didn't even, it wasn't him that started them or him that discovered them, but he used them to his advantage for his experiment, right? So you can see here, like, if someone hadn't discovered radioactive carbon, he can't do this experiment. If he didn't know how to do autoradiography, which is something that like Rosalind Franklin used when she was doing her trying to find the structure of DNA and so on, right? Like, so it's like people discover certain techniques, and then now scientists can be like, oh, that's really cool. Maybe I can use it for my thing, or maybe it works over here as well. So yeah, with that, with the combination of these two things, he was able to sort of figure out that there's this cycle of development in organic molecules. And that is all she wrote. We have come to the end.
Nice.
Of 8.3. I open the floor to questions.
Who's coughing?
I know, right? Corona.
What?
Let me tell you, let me say one more thing before you go, which is, where's the folder? Okay. What we would do normally is I would give you, what's going on? Normally, what you would do next is you would make a giant poster.
Ew.
This would be kind of like your task for the end of the term. And I've done it every year. The reason that you would do this is because it is an excellent way to go back through all of the different steps in cell respiration and in photosynthesis. And it also becomes an amazing resource for yourself for when it's time to study these things. So do I have a photo? No, I don't have a photo. At school, I have examples of past students' work. But basically what you would get is I would give you like an A4 or probably two A4s, and you'd stick them together. And you'd create this poster where the two concepts of cell respiration and photosynthesis at the HL level are linked, right? So you'd have all the processes going on in a chloroplast, in a plant cell over here. You'd have all the processes in a mitochondria, in an animal cell, or you could have them in the same cell, doesn't even matter. But it'd have to be a plant cell, I guess. And you would like allow for like flow of, for example, oxygen to go from one organelle to the other, and CO2 to go from the other organelle to across. So you're now connecting these two topics. And you would build a nice, like a really big poster that that links the two ideas together. So you could, these are just examples that I provided usually, and I'll put this up on iLearn as well. I can't really force you to do this, but I highly, 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 highly recommend that you like draw the whole thing out, right? So that you have this really big map of how these two things are not only the two separate topics, but how they're linked together with each other. Okay, so this is what I would normally ask you to do.
Okay.
I wish I had photos of the ones that people have done, but don't think I have them. Aside from that, That's all I've got. What is that?
Well, and B.
Huh? Oh my God. Well,